Welcome to Chapter 5. This is Section 5.1, Fundamental Trig Identities. Here are our objectives for this chapter. Basically, we need to become very familiar with different trig identities, and we will use our algebra skills to simplify trig expressions and to verify identities. This page is very important. I would recommend, if you haven't printed off a copy of the different fundamental identities, that you do so, because we will be referring to them a lot. Basically, in this section, I am just going to show you many examples so that you can kind of see some different ideas of how to simplify expressions and then how to verify trig identities. So let's just jump right into some examples. Here is our first example, and it says to simplify the expression. And once it's simplified, the final form should not have any fractions. So generally speaking, it's often best to rewrite these identities using their reciprocal identity. So for example, cosecant of x can be written as 1 over sine of x. Now cosine squared of x, I'm just going to leave that as is, or if you want, you can write it as cosine of x times cosine of x, and you can put this over 1. And then secant of x can be written as 1 over cosine of x. So from here, we can hopefully remember that when we are multiplying fractions, we multiply across the top and across the bottom. So we should be able to tell that a cosine of x and a cosine of x will cancel out. And then I'm left with a cosine of x in the numerator and a sine of x in the denominator. I know I am not done because my final form is written in a fraction. So I should remember that if I have cosine on top of sine, this can be reduced to cotangent of x. And this is it. So I have simplified this expression to this. Let's take a look at another example. Same thing. If I can use a reciprocal identity, I am going to go ahead and do that. So rewriting tangent of x, if I can rewrite everything in terms of sine and cosine, a lot of times that is helpful. Not always, but a lot of times. So tangent of x is going to be written as sine of x over cosine of x. Again, cosine squared, if you want to write it as cosine times cosine, you can, but you certainly don't have to. And then secant of x is 1 over cosine of x. So here you should be able to tell that cosine cancels, another cosine cancels, and we are just left with sine of x, and it is in the numerator, so we're done. Okay, so this one is a little bit different because we are starting off with a fraction. Don't be scared. Same rules apply. Do the exact same thing that we just did. So again, if you want to write cosine squared as cosine of x times cosine of x, you certainly can. But I'm going to show you an example of how you can proceed without doing that. Now, hopefully you notice that cotangent of x can be rewritten as cosine of x over sine of x. Okay, you might want to put the sine of x over 1. Now, looking at this, the numerator, I can't really cancel anything out there yet, so I'm just going to leave the numerator alone. But the denominator, I can cancel out sine of x. And then I'm left with a cosine of x down here. Well, cosine squared of x over cosine of x, this cancels out with one of these, leaving me with cosine of x. That's it. Okay, here, if you look at this example looks a little bit different than the ones we've seen previously. Here we just have one fraction. So what we're going to do is we are going to simplify this by getting a common denominator. Or what I like to say, common denominator. Okay, so looking at this, I only have one fraction, so it's pretty easy to identify what my common denominator is going to be. It's going to be the denominator that's there. So instead of writing 1, I'm going to represent 1 as tangent squared of x over tangent squared of x. Okay, so when I rewrite this, this becomes secant squared of x over tangent squared of x minus tangent squared of x over tangent of x squared. Okay, well, now that I have two fractions with a common denominator, I can write this as a single fraction with that denominator. So if I look at this now, remember I'll just subtract these two items. So it becomes secant squared of x minus tangent squared of x. Now, when you get to this point, if you see something squared, a lot of times you will want to see if one of the Pythagorean identities fits this bill, or you're going to want to see if it's factorable. Now, looking at this numerator, I can't just cancel out these tangents, because if I do it, I'll get back to right where I started. Okay, so looking at this, if you see something squared, see if it will fit one of the Pythagorean identities. In this case, it does fit a Pythagorean identity, but it's going to be a Pythagorean identity that's manipulated a little bit. Recall, tangent squared of theta plus 1 is equal to secant squared of theta. So in our case, our version is subtracting tangent squared from each side. So this results in 1. So this is 1 over tangent squared. Again, I do not want any fractions, so tangent squared can be, 1 over tangent squared can be represented as cotangent squared. Okay. Now, the only way you are going to get a hang of this is if you practice them on your own without looking at the answers. Okay, so I would just practice, and then refer to some of the answers. Okay, so here another one, and this is a fraction. The method we're going to apply in this particular problem is we are going to simplify by factoring. Now, if you are frightened of the word factoring, you're going to have to become used to it, especially if you are going to major in math, because factoring does not go away, ever. So let's take a look at this. I'm going to start by looking at the numerator. When I look at the numerator, I can see that I have a cosine of x in common. So I'm going to take out that GCF, cosine of x. And when I take that out, I'm left with cosecant squared minus 1. Because if I distribute this cosine, I will get back to where I started. Then in the denominator, I'm going to do the same thing. I'm going to factor out a cosine. When I do, I am left with cosine of x times cosecant of x plus 1. Okay, so we have a different sign here. The numerator is squared where the denominator is not. Now looking at this, I can see that both of these factors have a GCF of cosine of x. So I can cancel out cosine of x. And I am left with this piece here. Now we have a couple choices here, and we need to figure out what works. Now, part of you might be saying, oh, the numerator is a trig identity. And you're right, it is. In fact, the numerator is equal to tangent squared of x. And then we would have cosecant of x plus 1 in the bottom. Now, and again, that comes from the Pythagorean identities. Now, if you're looking at this, you really can't go anywhere from here. And you can pause this and try to play around with it and see if you can simplify this and have it be something kind of nice and neat without any fractions. And you'll find that it's pretty complicated. So what we're going to do is we are going to, this doesn't get us anywhere, so we're going to back up and we're going to come back here. This is kind of tricky to identify this. So if you, for my next step, if you're like, holy cow, how did she come up with it? Just bear with me, okay? This is something that's going to come up a lot, and you'll kind of start to recognize it. What I have here in the numerator is a difference of two squares. I have a perfect square, another perfect square separated by a minus sign. So in the top, I have a difference of two squares. You may recall that when I factor a difference of two squares, you get the same factors, but one has a plus and one has a minus. Cosecant times cosecant is cosecant squared plus 1 and minus 1. Then in the bottom, I'm just going to leave this cosecant of x plus 1. What do you know? I have a cosecant of x plus 1 and a cosecant of x plus 1, leaving me with cosecant of x minus 1. We don't want our answer to have any fractions, so this is our final result. Let's take a look at another example. I want you to remember that the easiest way to get the hang of this is by practice. Okay? Now, looking at this, there are a couple things you can do, and you might notice, oh, this numerator is a Pythagorean identity. I can write this as a negative tangent squared of t. You could factor out a tangent of t, and you're left with 1 minus secant of t. You could then proceed and cancel out one of the tangents, but you'll find that if you take this approach, you're not able to get anywhere with this. And you can keep playing along and trying to simplify it, but it gets messy real fast. So let's just say nah to this approach. You might go through some paper with this, and that's fine. So instead, let's take the same approach that we did before. So we're going to skip out on this, and instead, we're going to recognize that this here is a difference of two squares. Like I said before, this comes up a lot. So remember, with a difference of two squares, you have the same factors. One has a plus, one has a minus. So we'll have 1 plus secant of t and 1 minus secant of t. I will go ahead and factor out that tangent in the denominator. So again, I'm left with 1 minus secant of t. These factors cancel, so I'm left with 1 plus secant of t over tangent of t. Okay, well, here I can rewrite this as two separate fractions, and I refer to it as the Hart method. So I can write this as 1 over tangent of t. There's a plus sign, so plus, and then write a second fraction of secant of t over tangent of t. I call this the heart method because it makes a cute little heart here. You can't use the heart method on the reciprocal of this because it will result in a broken heart, and nobody wants that. All right, so let's continue to simplify this. 1 over tangent of t is the same thing as, cotangent of t. This second fraction, this is 1 over cosine and sine over cosine. The cosines cancel, leaving me with cotangent of t plus 1 over sine of t, which is cotangent of t plus cosecant of t. Sorry, I ran out of room, but that would be our final answer. After all of this practice that I've done and examples I've shown you, here are the guidelines for verifying trig identities. So what we've just done is we've simplified trig identities. And we're going to need to simplify these trig identities in order to verify different identities. So everything we've just done is leading up to verifying trig identities. So here are all of the steps. Okay, so now what we're going to have is we're going to have one crazy trig explosion equal to another crazy trig explosion over here. Okay, so basically two of the same things that we've just simplified. And what we'll want to do is we'll want to focus on one side of the equation. Typically, we'll focus on the more complicated side, but we'll keep the other side in mind so we know what we're working towards. And we're going to take that one complicated side and we are going to manipulate it like crazy and try to get it so that it equals the more simplified side. So these are some different ideas of what you can do when you simplify. You can consider your reciprocal or quotient identities. You can see if it's a Pythagorean identity or if you need to factor something or combine like terms. And like I was talking about before, you could also try to simplify things as much as possible with using sine and cosine. Now, just like before, the way you're going to get the hang of this is by practice, practice, practice. So make sure that after you see me do a couple examples that you pause the video and try to do some on your own. Here's our first example, and this is what I mean. We want to verify that this mess over here will in fact equal something a little bit simpler. So what I'm going to do is I'm going to take one side of this equation and I'm going to manipulate it like crazy. And oftentimes we will use the more complicated side. In this example, this side of the equation, or the left-hand side of the equation, is more complicated. This has a lot of the even and odd identities, which are located a few slides back. So remember, the only even and odd identities that are even are cosine and secant. So if you have a negative argument for cosine, it comes out positive. So this results in cosine of x. Secant of negative x, that comes out as a positive as well. But over here, these are odd identities or odd functions. So if you plug in a negative, out comes a negative. So this becomes negative tangent of x because we want a positive argument. And this becomes a negative cosecant of that positive x. I'm just going to leave the right-hand side alone, and I'm just going to manipulate this like crazy to see if I can end up with secant of x plus 1. Okay, so let's just keep trucking along. Cosine of x, I can't do anything with this, but secant of x, I can write this as 1 over cosine of x. Plus, over here, a negative times a negative is positive, so I know that I'm going to end up with a positive. But I'm going to rewrite tangent of x as sine of x over cosine of x. And cosecant, I'm going to write as 1 over sine of x. Now, hopefully you can see here that some things are going to cancel out. This cosine will cancel. This leaves me with 1 plus, over here, the sines cancel, and I'm left with 1 over cosine of x. Now, in the back of your mind, you always want to consider what you are working towards, and we are working towards secant of x plus 1. Well, turns out, if I rewrite this, I end up with 1 plus secant of x, which is the same thing as secant of x plus 1. So I have just verified this identity. Now, before I move on to more examples, I want it to be very clear that your answer to these problems, anytime you are verifying, your answer is your work. You can't just say, oh, secant of x plus 1. Well, I know that's what I'm working towards, okay? I know that's the goal. Your answer is your work. So, for those of you who don't like to show your work, you have to in problems like this. Here's another example. Here, I want you to notice that our more complicated side has 2 fractions, but the less complicated sign does not have any fractions at all. So we are going to start once again with the left-hand side, and what we're going to try to do is we are going to try to get 1 fraction instead of the 2. And then we're going to try to simplify that fraction so that it comes out of fraction form and takes on 2 tangent of x instead. So, to summarize, I'm going to combine my fractions. And remember, when I'm combining fractions, I need to get a common denominator, just like we did in a previous problem. So, in this case, I'm just going to use a common denominator of my current denominators multiplied together. So my common denominator is going to be secant of x minus tangent of x times secant of x plus tangent of x. Okay, so if this is the case, then what did I do to this 1 to get this common denominator? Well, I multiplied it by the opposite denominator. So I have secant of x plus tangent of x here minus, what did I do to this 1 to get this new denominator? I multiplied it by this. So I'm going to make sure I put the other denominator in parentheses, so secant of x minus tangent of x. Okay, now if your mind just exploded and you have no idea what I did to write this as a single fraction, you might want to kind of review getting a common denominator. Okay. So in this case, now what I'm going to do is I'm going to distribute this minus sign. So I have secant of x plus tangent of x minus secant of x plus tangent of x all over my common denominator. And I am not going to FOIL out this common denominator just yet. I'm just going to leave it as is. Oops. Plus tangent of x. In the numerator, I'm going to cancel the secant of x, and I'm left with tangent of x plus tangent of x. When I'm adding these, I get 2 tangent of x. When I multiply, I get tangent squared. Okay, now in the bottom, you may notice that these are the same factors, but one has a minus and one has a plus. This is a difference of 2 squares, but now we're working backwards. Notice how this keeps coming up. So I can rewrite this as secant squared, minus, because it's a difference of 2 squares, tangent squared. Now you may recall that I said previously, anytime you have some trig function squared, think if it falls into some form of a Pythagorean identity. Well, this here is a Pythagorean identity, and the denominator simply equals 1. Anything over 1 is itself. So, oh my goodness, this is what we wanted to achieve, and we did. So we are so happy. Again, all of this colorful work is my answer. Here's another example. I would recommend attempting to pause this and giving it a try. The more complicated side is the left-hand side. I'm going to try to manipulate this left-hand side so that it comes out of the fraction and ends up as 1 minus sine of x. If I can manipulate this so that I end up with 1 minus sine of x, I have verified that this equation is an identity, and I will be super happy. So what I'm going to do first is I'm going to rewrite everything in terms of sine and cosine. So I end up with the following. Instead of tangent of x, I'm going to write it as sine of x over cosine of x. You will see that here in my denominator, I can now write this as 1 fraction (1 plus sine of x over cosine of x). Now, in mathematics, we do not want a fraction within a fraction. So to eliminate this, I need to multiply the bottom by fraction. I need to multiply the bottom fraction by cosine of x. And whatever I do to the bottom, I must also do to the top, because it's like multiplying by 1. When I do, in the bottom, these cosines cancel. In the top, I'm left with cosine squared of x, because cosine times cosine is cosine squared. All over, the only thing I'm left with is 1 plus sine of x. Okay, so here you might be thinking, this isn't really getting me anywhere. I need to end up with something that is not a fraction. Well, keep plugging away. Hopefully a red flag went up, because cosine squared can be written as a Pythagorean identity. We can apply a Pythagorean identity that might help us eliminate the denominator. So let's just see what we can do. Now, cosine squared of x can be rewritten as 1 minus sine squared of x. Well, you know, we're getting closer, but this still doesn't help. Well, this again, is a difference of two squares. This is going to come up a lot, and you're going to want to be able to recognize it. Perfect square separated by a minus sign, difference of two squares. So remember, a difference of two squares, it's the same factor, but one has a plus, one has a minus. One plus sine of x, one minus sine of x. All over 1 plus sine of x. Holy moly, would you take a look at this? The 1 plus sine of x cancels out, and I am left with 1 minus sine of x, which is exactly what I wanted to achieve. Can you see how happy we are? Let's move on. Here is another example. This one is a little bit different than some we've seen before. If you look at this, I start with a fraction and I want to end up with a fraction, but the binomial in the left-hand side is in the denominator, and in the right-hand side it's in the numerator. So pick one of them and manipulate it so that you get the other. I will start with the left-hand side. So just rewriting this left-hand side. You might be thinking, well, nothing's squared, so I don't have a Pythagorean identity. What am I going to do to manipulate these? You might start rewriting in terms of sine and cosine, but you'll find that there's not a lot that you can do. So instead, in this particular problem, what we are going to do to simplify is we are going to multiply by the conjugate of the denominator. Now you might be thinking, holy cow, how would I have thought of that? Well, chances are you would not have, and that's why I'm here to help you. So remember the conjugate. It's the same factor except the sign changes. So the conjugate of the denominator in this case would be cosecant of x plus 1. We are going to multiply the bottom by this. Whatever we do to the bottom, we must also do to the top, so that this is like multiplying by 1, which does not alter our expression in any way. So when we do this, I will distribute this cotangent to get cotangent of x times, actually, I am not going to distribute. I'm just going to leave it like this for now. And this is why. If you do distribute, you will have to factor out the cotangent of x again. And you'll see what happens. In the bottom, if I FOIL this out, then the reason we are multiplying by the conjugate is so that we end up with the following. This gives me a cosecant squared of x. This gives me a cosecant of x minus cosecant of x minus 1. Okay, well, we're getting closer. Maybe you recognize that we either have a Pythagorean identity, which is helpful. So here, the top is this. The bottom, this becomes cotangent squared. And this is helpful because this will cancel out with this. And remember, look ahead to what we want to achieve. It is a fraction. In fact, it is this fraction after we cancel out a cotangent. And we are happy. So again, this was a Pythagorean identity. So there are just lots and lots and lots of examples here. Here is another one. In this case, we are dealing with natural logs. You may want to review properties of logarithms a little bit because they will come up, not a lot, but when they do, you don't want to be slapped in the face with having to remember all these identities again. So let's just take this piece by piece. You may recall, and again, I'm going to start with the more complicated side. You may recall that if you have a logarithm with the same base and they are being subtracted, that you can rewrite this as the natural log of sine of x divided by cosine of x. So that subtraction, you can rewrite the logarithm with the same argument, but with division. And then this is plus the natural log of cosecant of x. Now take a moment and see where we're trying to head. Okay. All right, well, these are all natural logs, so I can write this again as a single logarithm. Remember, this plus means multiplication, so I can write this as sine of x times cosecant of x all over cosine of x. Okay, well, now I'm going to rewrite this. So I have the natural log of sine of x times 1 over sine of x all over cosine of x. Now you need to show all of these steps because your work is your answer. Sine of x cancels out. So I am left with this, and hopefully you're noticing that we're getting closer to our goal, which is the natural log of secant of x. We made it. Example 10 is a little bit different. It says verify that the equation is an identity by manipulating each side of the equation independently. Now, when you look at this, you will see the left-hand side is a mess and the right-hand side is also a mess. So one approach you can use is you can focus on the left-hand side, manipulate it, and you'll end up with something that is not the right-hand side. Well, if you can manipulate the right-hand side so that it equals the same thing that you got on the other side, that works also. Okay, so let's take this approach and see what happens. So I'm going to start with the left-hand side. Looking at this, I see that I can factor out a sine of x. And I'm left with 1 minus sine squared of x all over cosine squared. Now hopefully that red flag went up and you thought to yourself, oh, this is a Pythagorean identity. In fact, this becomes sine of x times cosine squared of x all over cosine squared. The cosine squareds cancel out and we are left with sine of x. Now, I can't do anything else with sine of x. There's nothing I can do. And it doesn't equal this right-hand side. So I'm kind of at a standstill. So what I can do is I can move over to the right-hand side, see if I can manipulate that and end up with sine of x. If so, then I have verified the identity. Now, you guys are probably pretty good at math, but you are not good enough at math to make up math. So you need to make sure that you are using real-life algebra rules. So let's get started. Sine squared of x, I'm going to rewrite secant of x as 1 over cosine of x. And then I'm going to write the denominator as sine of x over cosine of x. Well, these both have a denominator of cosine of x. If I multiply the top and the bottom by cosine of x, they will cancel out. And this leaves me with sine squared of x over sine of x. Well, this will cancel out with one of these, leaving me with sine of x. Oh my goodness, sine of x does equal sine of x. We have just verified this equation is an identity. by manipulating each side independently. Not so bad. Okay, so this information is a little bit different than what we've done so far in this section. Basically, what I want to show you is that sometimes our trig functions are written as algebraic expressions. For example, if I have this triangle here and I apply SOHCAHTOA to figure out my trig identities or my trig expressions, you'll see that some of these sides are algebraic expressions instead of numbers. Well, we will still do everything the same way as before, but we just want to be cautious that if I want to find secant, for example, secant is going to have some algebraic expression. Okay, so here's a type of problem you will see in a situation like this. It'll say, write the given algebraic expression as a function of theta, where theta needs to be in between 0 and pi over 2 by making the given substitution. So I've said, hey, we are going to start with this radical, but instead of x, substitute for sine of theta. Okay, so all I'm going to do is I'm going to take this and substitute this in. When I do that, I end up with 16 minus 4 sine of theta. Squared. Sorry, x is squared, so all of this is squared. My bad. Okay, now, some of you might be thinking, oh, at 16, you can take the square root of that, and the second term is squared, you can take the square root of that, and boom, this becomes 4 minus 4 sine of theta. Well, no, you can't just take the square root of things separately unless it's multiplication or division. That's highly illegal. Instead, what you need to do is manipulate it algebraically using real algebra rules. Take baby steps. First, square all of this. So we end up with 16 minus 16 sine squared. Now, notice you have a 16 in common. Take out that GCF. When you take out 16, you are left with 1 minus sine squared of theta. Now, this is multiplication, so you can take the square root of these separately, but before you do, notice that this is a Pythagorean identity. It comes up all the time. So this is equal to 16 times cosine squared of theta, which is the same thing as taking the square root of 16 times the square root of cosine squared. I can take the square root of these individually now because it's multiplication and not addition or subtraction. The square root of 16 is 4. The square root of cosine squared is cosine of theta. Because theta is in between 0 and pi over 2, I will have the positive square root. My algebraic expression is now a function of theta because theta is involved. Let's try one more of these. Okay, so same rules, but now I have two x's and I'm going to substitute tangent of theta in here. So this becomes the following. 3 tangent of theta, all of this is squared, plus 9, all over 3 tangent of theta in the denominator. Now, I'm not going to just take the square root of stuff. I'm going to first square that first term. 3 squared is 9. and then I have tangent squared of theta. Just that is under the radical. The denominator is not under the radical. I'm going to take out a GCF of 9, and when I do, I'm left with tangent squared plus 1 in the top, under the radical. Pythagorean identity here, this is secant squared. So I have the square root of 9 times secant squared, oops, all over 3 tangent of theta. In the top, since I have multiplication, I can take the square roots of these separately, and I end up with 3 times secant of theta, all over 3 tangent of theta. The 3's cancel, but now I want to rewrite the secant and the tangent. So this is 1 over cosine of theta and sine of theta over cosine of theta. You don't want fractions within fractions, so you can multiply the top and the bottom by cosine of theta, and you will find that these cancel out. 1 over sine of theta reduces to cosecant of theta. Some of you will love this material and others will not like it at all. But the key to being successful in this section is practice, practice, practice without looking at the answers while you are doing your work. Good luck.